expand our means-based analyses into ANOVA, and then sort of eventually we'll get back to some more pairwise stuff here. I guess before I get going, other questions about where we're at in the trajectory of class or anything along these lines? Okay, I just in terms of your own sort of process of planning out sort of when to spend time on problem sets and stuff like that, honestly, it's probably going to take us 3 weeks to get through all of this material. There's just a lot of stuff, so I want to make sure people are strong in the building blocks of ANOVA and things like that. So we'll have this, the power and confidence interval set due next Friday, and then you're probably going to get another week in between the ANOVA set, and so before then, before it's due, we probably won't finish up with all our post hoc stuff until 2 weeks from now. So that gives you a little bit of time. What I'm going to go through and do though is I'll probably go through and post this ANOVA set early so that you have it. I just am always concerned about stressing people out if they've got 2 problem sets hanging out in their docket. Don't worry about that. It's just sort of there so you can take a look at it and get an early start on stuff. Sound good? Okay, cool. So, this is a big chunk of slides, but I'm going to go through and start out to give you a conceptual basis of sort of this ANOVA process when we have more than 2 means, thinking about things a little bit differently. I start showing you how we go through and partition variability within and across treatments. This is one of these things that I sort of struggle with back and forth from a didactic standpoint. Is it useful to teach you guys how to run ANOVA by hand? Probably not. You're probably never going to go through, don't shake your head, it is useful, otherwise I wouldn't have you do it. But in terms of as we start to move forward with stuff, right, as you start to get into more complicated analyses, being familiar, at least sort of recognizing that, hey, this total piece of the pie is being sectioned off into this area, is going to be helpful in terms of calculating miscellaneous statistics and sort of picking up some other stuff. We'll go through ANOVA calculations, a general linear model approach to ANOVA. We'll touch on that quickly. This is a good set up the stage for regression stuff that we'll do next semester. Effect sizes, confidence intervals, and then we'll finish up with follow-up tests. That's really the big, the ANOVA, the omnibus piece of things is actually pretty easy. It's not that much to it, right? It's going through and deciding how I'm going to go then through and take that omnibus test, break it down, and figure out exactly what's happening with things. Okay. So, as a review, because I remember this being confusing. We get sort of lots of different tests and trying to figure out when do I use what and how. Remember, a single sample test is a comparison of a single sample mean to some known reference population mean and standard deviation. Our single sample test, this is a comparison of a single sample mean to some known population mean or some reference point when we don't know what the variance is or the population standard deviation. Independent sample t-test, this is when we're comparing 2 different samples drawn from populations with unknown values. And then our paired sample test, this is the analysis of mean difference scores across a couple of different assessment points within a single sample, although I've asterisked this. Chris C, why do I asterisk paired sample here? Does it have to be one sample of people measured across multiple assessment points?
You can pair different samples.
Yeah, we can have different types of paired match designs that we can then reasonably use with our single sample tests. Okay. Problem runs into what if we need to compare more than 2 means, right? Oftentimes, let's say we're in a pharmaceutical trial and we have drug A, drug B, drug C. How do we go through and test those, right? If I have, we're to do this with an independent sample t-test, I've got 3 different tests, right? I've got A versus B, B versus C, A versus C. That gets at these 3 differences, but it's kind of limited in terms of I then have to go through and run multiple tests to go through and sort of get at all the differences there, right? And what I might be interested is overall, in general, are there differences across sort of this group of conditions or these different populations? And so what we can use is our ANOVA, our analysis of variance. What we're going to go through is we're going to take and look at differences in some dependent continuous outcome across 2 or more groups. Okay, so in a one-way ANOVA, how many independent variables do we have? Chris? Yeah, just one. And this is confusing, right? Because there's like, well, we've got condition A, condition B, condition C, right? But we don't have 3 independent variables, just one independent variable. It's just the one categorical independent variable. So what we're doing essentially, functionally, and we'll talk about this from a GLM approach, what we're looking at is one categorical IV and looking at the relation between our categorical IV and our continuous dependent variable. This is going to help start making some of the effect sizes that we're using for our omnibus tests make a little bit more sense. Okay, so our ANOVA procedures are nice in that they're kind of more efficient. You sort of get it all in one shot, and we kind of avoid complications with type 1 error by just running a bunch of tests over and over. But really, where the strength of this is, it gives us more flexibility in designing experiments, right? So that not everything has to fall back on a 1,000 different pairwise tests, right? So it gives us a little bit more ability to be creative in sort of how we're going about testing our hypotheses. So not unlike our t-tests, what we've got is we've got, say, 3, 4 K different populations, distinct populations with unknown parameters. We don't know what the means of these populations are on whatever we're measuring. We don't know what the variance is for these populations. But what we can do is we can go through and we can sample these, right? And so we go through, we draw a sample from population 1, a sample from population 2, a sample from population 3, and then what we do is we're going to go measure the characteristics of that sample, and then based on that, we're going to go through and try and infer something about likely differences or similarities across the respective populations, okay? And so we can have 2 possibilities, right? Always 2 possibilities. Remember that we could see results just as a consequence of random fluctuation, right? Even if these populations did have the exact same mean, the exact same variance, it would be unlikely that we would get exact same values for each one of these means, right? So it's possible that differences that we're seeing across these 3 scores, a mean of 23, 28.5, and 20.8, it could be that these are due just to random variability, just random sampling. This is just sampling error, okay? Right? This is a good example of sampling error. Let's say the mean of each one of these is 23, right? What we've got is the difference between my sample statistic, my population parameter. What I'm just seeing here is sampling error, right? Doesn't mean that my sample is biased. I may have the best sample. I may have the perfect sample of n equals 15. It's just it's always going to be a little bit different there, right? So I could be seeing random fluctuations, or I could be detecting sort of the difference that I'm seeing is actually due to some underlying difference across these populations, right? These samples are different because the populations I'm drawing from have different population means, right? And what we're trying to do with our ANOVA model is trying to tease this apart. How do we go through and say, based on the information that we have, what are we going to say is likely due to just sampling error, just random differences, or the influence of maybe unobserved or unmeasured factors, and how much of this is driven by our actual effect. Okay. So this is kind of a recap of, so we've been through this in terms of our other paired tests, but questions about sort of this. People are feeling pretty good about sort of this general concept. Starts becoming important again when we're dropping back. We're talking about confidence intervals and effect sizes and population effects and things like that. Okay, so some basic terminology. ANOVA, we call the same things different things, which makes things confusing, but just so we're all on the same page. We're talking about a factor. This is our categorical ID. This is our indicator of our group. So a one-way ANOVA, one factor, right? We have one independent variable. It can be experimental condition, year of high school, sort of racial, ethnic background, something like that. That's what we're looking at, right? Level, this is our individual conditions or categories within our factor, right? So I can have condition 1, 2 versus a control, freshman, sophomore, junior, black, white, Hispanic, Asian, right? The level is sort of the categories within our factor IV here. And so for our one-way ANOVA, what we're looking at is a single categorical factor, looking at the relation between that categorical factor and some continuous dependent outcome, right? And our question here is, are we seeing reliable differences in outcome across our different levels of our independent variable? People comfortable with this? Sort of, everybody have sort of previous exposure, at least at some point in your distant history, with ANOVA models and things along those lines? Okay, good. So why don't we just use a bunch of t-tests, right? Why don't we just sort of t-test the hell out of stuff? We will eventually, but sort of off the bat, right? So the concern is that when I set my risk of type 1 error, right? I do this on the front end, right? And let's say, so I go through and I want, based on over an infinite number of replications, I would want to make a type 1 error only about 5% of the time, okay? 1 out of 20, 5 out of 100, okay? Tomorrow, remind me what type 1 error is.
That we find significant for a relationship when nothing's actually there.
It's okay to say significant. Right? Yeah, you're like, it's okay, come across the desk. Yeah, I mean, sort of the idea is that I'm claiming evidence for an effect when there is no effect to be had, right? And so I go through and I set this up, right? And so if I have, in this drug trial, I've got 3 different groups, right? Condition A, condition B, and condition C. If I were to look at this with independent sample t-tests, it would require me 3 different t-tests to make all possible pairwise comparisons, right? I'd have A versus B, A versus C, and B versus C in order to get all of those, right? The problem is each one of those is going to be conducted at alpha 0.05. And what happens as we start to accumulate these tests, we accumulate type 1 error. And so across these 3 comparisons, the likelihood of us making at least 1 type error across this set of comparisons approaches coefficient C times alpha, where C is the number of independent comparisons. Okay? So for type 1 error for these 3 independent sample tests isn't 0.15 for the whole collection, or is 0.05 for the whole collection. It's about 0.15, right? So I've got, say, a 15% chance of claiming within this set of comparisons, making the claim that one of them is statistically significant, assuming that all 3 of these comparisons are false. Okay, so assuming that the null is true for each one of these, right? That there is no difference across any of these groups. My risk of committing a type 1 error now is at 15% instead of 5% with the individual selection of each one of these. Okay? And so what we do in ANOVA is we go through, and the idea is, from a sort of old school method standpoint, the idea is to go through and look at differences across these 3 groups simultaneously, all at the same time. So instead of running 3 different tests, let's just do 1 test, try and capture overall, do I see evidence of differences across these conditions? Let's just run 1 test, and then we avoid compounding type 1 error with the running of individual differences. Okay? Now, this isn't a perfect solution. We'll talk about why that isn't. This isn't a perfect solution down the road. But in general, if we're just trying to run out and see, do we have evidence of something going on in here, our omnibus ANOVA test can be kind of helpful. So questions on, so we'll get more sort of later in this lecture, we'll get more into this type 1 error issue, but questions with any of this stuff? Okay. So our hypotheses for our one-way ANOVA. Null hypotheses is just kind of the same thing as we've been doing before. Mean 1 equals mean 2 equals mean 3. Here we'd say the mean of the populations from which each sample is drawn are going to be equal. I'm saying that each one of these all functionally equivalent on whatever it is that we're looking at, right? We can also just break this down into, this isn't just a general GLM type of approach. We can say there's no effective X on Y, which is kind of tricky, right? Because we tend to think about sort of like in bivariate example, right? So relation between height and weight and things along those lines. But remember that population 1, population 2, population 3, these just represent levels or different populations of some categorical variable, right? Race, ethnicity, experimental condition, sort of the class or something like that. This is just still one IV, right? So we're saying that there is no association between our independent variable and our outcome. Okay? Now our alternate hypothesis is just that one population mean differs from the other, right? There's no specific alternative hypothesis in ANOVA, right? Because there's a lot of different ways that these populations may differ, right? So CJ, tell me some ways that if this is my null hypothesis, give me some examples of alternative hypotheses.
One of the means differs just because of the sample that you chose,
Okay.
being an outlier.
Okay. All right. But let's say it's not an outlier. Let's say there really are true population differences. How many different ways can this omnibus, or excuse me, this null hypothesis be wrong? Anybody help them out?
9?
9? How
No,
did
6.
6. How did you get 6?
I don't know, 3 factorial.
You actually might be right.
Someone check it.
Right? Well, so which ones did we talk about already? So I could have 1 is not equal to 2, right?
It's not equal to 3.
I get 1 not equal to 3. I have 2 not equal to 3. So there's 3, right? How else can this be not correct?
1 does not equal 2 does not equal 3.
What's that?
1 does not equal 2 does not equal 3. So they're nominally equal.
Oh, yeah. So we got 1 greater than 2 greater than 3, right? We got that, right?
1 equals 2, but 3 doesn't equal 1 and 2.
Yeah, right. If we start getting into what we'll talk about in terms of contrasts later, right? That the combination of 1 and 2 is different than 3, or the combination of 1 and 3 is different than 2, right? So there are just a lot of different ways that this null hypotheses could be false, right? And so when we're trying to specify our alternate hypotheses, I can't provide the statistical notation, the specific alternate hypotheses. What I can say is that at least one population mean differs from the others, or sort of either individually or within combination. And so if I do end up rejecting the null hypothesis, essentially what I'm saying is that these data are unlikely assuming equal population. And so you just getting back into that whole null hypothesis testing framework stuff. Okay. So what we're going to run with our ANOVA is what we call an omnibus test. Okay, people familiar with this term? People have heard this before? Okay, omnibus test just means that is just referring to an overall level of significance, right? Somewhere in there, right? Something's different, right? There's something in there. As you're on storage wars or something like that, it's relative. So the thing on the storage unit thing, I don't know. It's a win. There's something in there somewhere. I don't know exactly where it's at, right? So what we're saying here with this omnibus test, if we get a significant omnibus test saying that at least one of these means systematically different from the rest, but our omnibus test doesn't tell us how, doesn't tell us where that difference falls. That's what we have to do with follow-up tests and things along those lines that complicate this whole process tremendously. But people get sort of a general feel for the omnibus test, how we're going to go through and sort of approach these ANOVAs. Okay, so for our test statistic, we're going to use a different test statistic that follows a different distribution. Okay, now when we just have two means, right? We've got two groups that we'll want to compare. What we can do is we can run our t-test, right? And conceptually, our t-test is just taking in the numerator. We've got the observed difference between means, and in the denominator here, the expected difference, assuming that the null hypothesis is true. So what is the expected difference in means, assuming the null hypothesis is true? What's that? Exactly the same. But even if my two populations are identical in terms of their means, I'm going to still get some differences when I go through and sample. What do we call those differences that we would expect? Well, where's in the denominator of your C-test? What's that?
Standard error?
Yes! Fantastic, right? Yeah, it's your standard error. Like, how much of a difference would we expect just due to random sampling, right? And what happens, Chris, if the difference that we see is considerably larger than the difference that we would expect just due to random sampling differences? What's the consequence for our statistical test?
It increases your T-score.
Yeah, right. What we do is, well, it increases our T-score. Our T-score goes up, our test statistic goes up, which means I'm more likely to make what decision in terms of my findings.
I just have 2 error. So I have it all backwards.
Okay, so as my test statistic gets larger, what am I more likely to do?
Reject them all.
Reject the null hypotheses, right? Again, basically, as my observed difference start to get increasingly larger than the differences that I would just expect due to random variation, my standard error here, right? Basically, my data are becoming increasingly incompatible with this null hypothesis, right? If under the null hypotheses, if my standard error is 3, right? On average, I would expect about a 3-point difference between these groups, and I found a 10-point difference. And that suggests that these data are generally incompatible with the null hypothesis of equal population means. Okay? Our F statistic is going to do basically the same thing, except now instead of looking at differences, we're going to be talking about variances. Okay? When we're thinking about variance within the context of ANOVA, anytime you hear variance, you should be thinking differences. Okay? Basically, I can't calculate a difference score if I'm dealing with more than 2 groups, right? I've got 3 groups. I've got 3 groups. We've got, let's say, 3 groups, all right? Nick, how do I go through and calculate the difference, one difference score between all 3 groups? I can't do it, right? And so the logic underlying my T statistic starts to fall apart. So I'm kind of at a loss, right? Well, what we can do is we can go through and use variability as a proxy for differences across my groups. And then what I can do is use the same basic ratio format that I use for my T statistic to calculate an F statistic. What I'm going to do is I'm going to look at the differences between my sample means and divide that by the differences expected if the null hypothesis is true, right? So I'm going to take this one number, this index of differences across my means, across my groups, and I'm going to look at it, compare it to the differences that I would expect if the null hypothesis is true. If these 3 populations all have the same mean, how much differences would I expect to get in samples from those respective populations? If the variability I get across my means is much larger than the variability I would expect under the null hypothesis, what am I likely to do or conclude in this scenario? You should.
I'm sorry, can you say that again?
Yeah, if the variance that I'm observing across my means is much greater than the variability I would expect from those means if the null hypotheses were true, what am I likely to do based on this test statistic?
Same thing as the test, right?
What's that?
Same thing as the
Yeah, and so tell me what that is.
So it would be more likely to reject those.
Exactly, right? The differences that I'm seeing in my observed data far exceed what I would expect if this is just random error, and so I'm much more likely to conclude evidence for differences across these means, okay? So, looking at our mean differences here, okay? Here I've got 2 different sets of data. I've got set 1 and I've got set 2, okay? In set 1, differences in my means, I've got a mean of 20, mean of 30, mean of 35, with a variance of 58.3. Set 2, 28, 30, 31, variance of 2.3. Chrissy, which one of these sets am I seeing more differences across my means?
Set 1.
Yeah, how did you know that?
The variance is higher.
The variance is higher because you're a quick guy and you figured it out, right? Well, what most of us are going to do is we're going to look at these means. We're going to say these are sort of discrepant, right? These are very, very far apart, right? But to go through and try and capture and sort of communicate those differences in a single statistic is hard, because I can say, well, there's a 10-point difference here, there's a 5-point difference here, there's a 15-point difference here, right? There's a lot to go through and try and communicate those differences. Or I can just tell you the variance, right? Now, variance in and of itself doesn't communicate a whole lot of information because it doesn't sort of tie into necessarily a specific unit. But if I can go through and look at the variability here relative to the variability here, assuming that we're measuring the same thing on the same scale, right? So which one of these is going to suggest to me greater differences across my set of means?
Set one.
Set one, right? And so what we're doing with ANOVA, and so this is, it can start to be confusing until you kind of get your hands around sort of this idea that when we're talking about ANOVA, variability or variance means differences. That's indicating differences across individuals, across groups, right? And so what we want to do is we want to take this and partition it out in ways that help us make some conclusions. So when we're running through our ANOVA models, our primary goal here is to take total variability of the sample, all the variability, the whole piece of the pie that we're seeing, and start to chop it up and put it into different places to try and detect whether or not we're seeing evidence within these data of systematic differences across our groups. Okay? And so with our one-way ANOVA, the simplest case of this model, what we've got is we're going to go through, we're going to partition things into between treatments variance and within treatments variance. Okay? This is where we're trying to separate everything out into. So between treatment or between condition variance, if treatments go to classic ANOVA term for different groups, right? Differences across our groups. Again, this is sort of using that this temperature handout, that ANOVA handout I gave you guys, if you haven't pulled that out, because we'll use it as a nice reference. But what we've got here in this example is looking at learning performance based on the number of problems solved based on room temperature, right? The hypothesis being that how hot it is in a room might start to have systematic impacts on your general performance, right? And so maybe we're aspiring IO psychologists or something like that, and we want to optimize office performance, right? So we're trying to figure out what to set the thermostat to. And so we've got an experimental design where we have just a small study where we have in condition 1, people at 50 degrees. Who wants to work in a room at 50 degrees? That seems chilly. We've got a room at 70 degrees. That seems nice. We've got a room at 90 degrees. Who wants to do, who'd rather be at 90 than 70?
Not enough.
Yeah, I do. Sorry, my greatest fear is being too hot. I'm talking therapies and things, so I was concerned about being too hot. I don't do well in the South. It's uncomfortable. I get fussy. Right?
It's a nice
so,
place.
What's that?
It's a nice place.
Where are you from?
North Carolina.
North Carolina, right? That's south-ish, right?
That is south.
It says North Man, I don't know.
I take offense.
Okay, so what we're looking at in terms of accounting for it, so in this design, we've got 1, 2, 3 conditions, right? And we're looking at average performance here. Average performance, number of problems solved. In the 50-degree room, we've got 1 problem solved on average. 70-degree room, 4 problems solved. 90-degree room, 1 average, 1 problem solved. And so these are the differences that we're interested in, right? The differences in average performance across our different groups. And so how do we understand these differences? One thing that could be going on is that these differences are a function of the actual groups or some treatment effect, right? So I've gone through, and what's driving these differences across these 3 conditions is the temperature in the room. I've gone through and I've put people in an uncomfortably warm, uncomfortably cold room, and then I put people in a sort of a nice, sort of reasonable human temperature room and looked how they perform. What might be driving these differences is this actual room temperature, right? But Other things that might be going on here, there could be random non-systematic differences, right? I might have sort of just person level differences that kind of come up, right? I've got 5 people in each condition. Let's say I truly randomize people to conditions 1, 2, and 3, right? Now I've gone through and done this at random. Nick, how likely is it that I'm going to see no differences in treatment 1, treatment 2, treatment 3, based on age, gender, intelligence, GPA, things along those lines?
I mean, there's a chance, but you know.
There's a good chance. With only 5 people, there's a real good chance that we're going to see systematic differences, right? When we identify, and I'm going to have you guys read a paper on this, right? So I've randomized people to my different conditions. That's good, but you're still, unless you've got like cell sizes of 40-ish, 50-ish, it's still probably likely you're going to have some sort of systematic differences across those, right? Randomization only works with larger numbers. With small samples, I'm almost certainly, it's very likely that sort of treatment 1 is just all men, and just truly randomly, just all men got randomized there, right? So we can see just random non-systematic differences due to our randomization procedure, individual differences, experimental error, right? Maybe the RA that was running treatment 1 wasn't very good, and the people who were, or the person who was running treatment 2 was just actually giving people the answers, or sort of giving people winks and nods and stuff like that. Who knows what the hell's going on with our stuff at the time, right? So we can see individual differences, experimental error, and then systematic differences unrelated to grouping factor, right? There could be other things that are systematically different across here that aren't random, they're just not included on our model, right? And what do we call any systematic difference that isn't accounted for in our model?
Something there.
Yeah, it's just error, right? It doesn't matter. Like I could go through, if I go through and let's say I want to look at differences in weight across men and women, right? And I go through and I sort of find that on average, sort of men weigh more than women, right, in terms of body mass, right? What's probably another factor that I need to be taking into account? We're talking about the physical mass of individuals across men and women. Yeah, height, right? That's a systematic factor. My men are probably going to be systematically taller than my women, right? But if I'm going through and I haven't accounted for that, any variability that I'm seeing as a direct function of height, that just gets chalked up in the error term, right? And so this starts to become important when we start talking about regression and ANOVA models, things like that, thinking about what other factors that are important that we should be including in our models that we haven't, because if there's systematic things going on that's influencing our outcome of interest and we haven't measured it, then that just gets chalked up with error, okay? So our differences here are going to be due to some combination of systematic differences based on my treatment effect, random systematic or random non-systematic differences, and then stuff that I haven't gone through and measured. Okay, Chris, what am I seeing between group differences in these data?
Where are you seeing it?
Yeah.
In the ANOVA?
What's that?
In the ANOVA.
in these data, don't
Oh.
like, you're just saying words at me.
It's my usual strategy, but it's not paying off.
Just throwing out buzzwords.
Standard error.
Standard error. Right. Where is? Call Fred.
Yeah, I think I got it.
No, so if we're just looking at these data, right? And so I want to go through and I want to look at the difference, the impact of temperature on performance. Where am I seeing differences in performance based on temperature?
Oh, in the different groups.
Yeah, my group meetings down here, right? So I'm going through and I'm taking a look at the differences across my individual groups, and so looking at this as evidence of my between group differences. Okay. People comfortable with our between group differences, what we're looking at here. Okay. We also have within treatment differences. Okay. Chris, I'm sorry.
It's fine.
I asked you a question and then you told me something and I yelled at you for it. Right?
It's
It's
fine.
It's not a good way to build a relationship. All right. Looking at within treatment differences. This is within group stuff. Okay. Now, for each condition, right? Everybody in treatment 1 is getting the exact same thing. Everybody in condition 2 is getting the exact same thing. Everybody in treatment 3 is getting the exact same thing. Okay? So because of this, Nick, if temperature was the only thing that determined performance on this task, what would I expect to see in terms of the scores within each group?
They would just be the same.
They're going to be identical, right? If treatment is accounting for 100% of the variability in performance in this, and everybody in treatment 1 is getting the exact same thing, everybody in treatment 1 should have the exact same score. Everybody in treatment 2 have the exact same score. Everybody in treatment 3 should have the exact same score, but they don't, right? And so what ends up happening is because within treatment 1, these are all people who completed this task in 50-degree weather, I'm still seeing differences going on in here. And because I don't know what this is accounting for these differences, this is going to be my error. This is going to be individual differences. This is going to be experimental error. This is going to be variability in my outcome of interest. It's not explained by my procedure. It's not something that I've gone through and measured. And if I haven't measured it, it's due to error. Okay. So where do we see, Sally, where do we see within group differences in the data here? Yeah, say it. I'm getting your sort of your gesturing. Where are we seeing within group differences?
Would it be, because I want to say between, but between like the treatments or?
Okay, so this is our between treatment variability, or between the treatment differences. Where's our within treatment differences occurring?
Within the actual
Yeah,
treatment.
within each one of these, right? So based on this, if my grouping variable perfectly accounts for, if there's a perfect causal relation between my categorical IV and my outcome, then everybody in treatment 1 should solve one problem, right? Everybody in treatment 3 or treatment 2 or condition 2 should solve 4 problems. Everybody in treatment 4, condition 3 should be solving 1 problem, right? But they're not. There's variability there, and so this is where my error is coming from. This is stuff that I'm saying I don't know. It's probably some combination of systematic and just random stuff, but this is the error that that I'm saying, or quantifying error within each one of my groups. Okay. People kind of seeing where we're getting sort of between group variability, what that means, or how we're interpreting that, and within group variability and how we're treating that stuff.
I have a quick question,
Yeah.
I think. So if you're doing ANOVAs with this within samples, would you just be doing one ANOVA within the sample? Oh wait, no, never mind. I got it.
You got it?
Yeah, I think so. So if it let's just say if it was like one person doing like 3 things,
Okay.
and you measured after each of the things, that would be an ANOVA.
Right. You're jumping ahead into like April of next semester.
Cool.
Yeah. But no. Your head's in the right place. What we're doing is we can take this sort of basic framework and start looking at within subjects ANOVAs, right,
Okay.
or repeated measures ANOVA models, where we're having the same group of people go through and complete different conditions, right? And then we can go through and cross that with have between group conditions and within subjects assessments, and then we've got mixed factorial designs, and that starts to get sort of complicated. But we'll tackle the one way between group ANOVA first, and then jump into that.
All right.
That help?
Yeah.
Okay. Cool. All right. So one thing you want to be thinking about, just and this is precursor for something we'll talk about a little bit later on today, and then also next semester when we get into some regression stuff. But if, let's say I have a sample of much greater than 5, let's say this is 100. No. Let's say I've got a sample. I've got big cell 50. Okay, and my mean here is 30, okay? What happens,
Standard error?
not standard error, just regular error,
Oh.
okay, right?
Keep putting a word in front of error.
So,
Tell me what you want.
right?
Say error, not conceptual economy.
Just error plus standard, right? Sure, have give you all the standard error titles, just like pop up, stock response, right? Within this, if this is everybody who's getting the exact same thing, right? Anybody who doesn't have a score, the difference between anybody's score and 30, what do we call that? This error, right? And so when we're thinking about this, starts to become important when we're going through and we're looking at our screening procedures, right? When we're looking at our distributions of scores within each different group. If our grouping variable accounted for the 100% of the variability in our outcome, should we have a distribution of our, in our sample data? No, everybody should be exactly the same, right? And so as the moment that not everybody is exactly the same, what is that sampling, that sample distribution represent, CJ?
Error.
It's just error, right? So what I'm saying is, right, is you're thinking about this is just as a distribution of errors, right? Because if it was perfectly, if my grouping variable was perfectly accounting for my outcome, and I was measuring it without error perfectly, anything that's sort of not exactly on top of one another, and so this is where when we start to get into regression models, when we're talking about things like homogeneity of variance and things like that, it's actually homogeneity of error, and it's sort of the same type of thing that we're talking about a little bit later on. So just kind of tuck that away for, that's a sleeper cell to explode at some point down the road when we sort of come up with stuff, okay? All right, so talking about here, so it gets us back to the F ratio. So primary test statistic for ANOVA is a ratio of two different variances, our between treatment variance and our within treatment variance, okay? And so this gives us a new statistic, right? Not our T distribution, our T statistic that we know and love. Now we've got an F distribution. F distribution is the ratio between the within variance, right? Conceptually, what we can think about from an F, think about this as our observed group differences divided by the differences that we would expect under the null hypothesis, right? Because even if the null is true, even if these populations have identical means, we're still going to expect when we sample from those to see some differences across these means, right? And this is being our within treatment variance or our within condition variance. This is capturing just general differences, right? And so we can also think about this conceptually as a ratio of our systematic effects plus random differences over just random differences, okay? So again, two possible scenarios here. One, I've got no systematic group effects, and the differences between our groups entirely due to error, okay? Really, truly, these populations I've drawn from all have identical sort of mean values, right? And so my systematic effects are 0. So the only differences that I'm seeing across my groups should be about the same as the differences that I'm seeing within groups, right? So if everybody in population 1 is coming from a population with the same score as everybody in population 2 and everybody in population 3, the differences that I'm seeing within a condition should be about the same differences that I'm seeing across conditions, because we're coming from different populations, but those populations all have the same mean and the same variance, and so we're expecting everything to come out. So what I'm going to end up with is an F ratio of about 1, right? So here the differences I'm seeing across my sample means is about the same amount of differences I'm seeing within people within a group, and so we're going to go through, we're going to get an F ratio of about 1. On the other hand, what we might have is that the populations that we're drawing from are actually systematically different, right? I am drawing samples from populations having different means. In this case, I'm going to get some level of systematic effects plus random effects, or random differences over random differences, but these two things are going to cancel each other out, and so what I should end up with is some F value that's systematically greater than 1, capturing, hopefully, in the best case scenario, these systematic effects that I'm getting across these samples drawn from different populations. People, how are we feeling with sort of conceptually thinking about this. And I think it's important because it sort of, this starts to help take sort of this out of just the realm of just cranking out numbers and starting to understand conceptually what we're actually capturing with some of these statistics, so to sort of kind of demystify it, and particularly if I'm seeing something that's gone sideways with things being able to detect it before sort of get too far along and stuff. We'll kind of see how these ratios are working from a conceptual level. Okay. All right. So summary of variability here. We're working with our total variability. This is the total piece of the pie. And what we're going to try and do is we're going to take this and try and separate this into our between treatments variance and our within. Right. Between, this is going to get differences due to systematic differences and just chance. Within, this is just sort of non-systematic differences due to variability and chance. And so we can go through and separate these out and use this to construct our test statistics. So one thing before we get into the next piece of things, remember, so going way back to the beginning, that our sum of squares and our variance, these are all just measures of variability across scores, right? Sum of squares is going to be the sum of squared deviations from the mean. If I'm talking about a deviation score, what am I talking? What am I talking about in terms of deviation score? Got it?
It's how far north from you.
Exactly, right? And so this starts to become important, right? When we're talking about, we're going to be working with deviation scores a lot throughout this semester and the next. Any deviation score just means the difference between some number and some other number, right? It's just a deviation, right? We can have different deviations. When we start to work through this, we're going to have deviations from the grand mean, right? So everybody's mean, the mean of everybody. We're going to have deviations from my group mean. We're going to have deviations of my group mean and the grand mean. And so anytime we're talking about deviation scores, it's just some difference, right? And so remember that our sum of squares, when we're calculating sum of squares for a sample of data, this is just the difference between each individual score and the mean of that group, right? That's going to give us our deviation. We go through, we take those sums, we sum up the squares of those deviations. Why do we square them?
So that they're positive.
Yeah, because otherwise it just sums to zero because it has to, right? But that measure, that sum of squares is just a measure of variability. It doesn't mean a lot intuitively. Like I can't say, Siley, here's a sum of squares of 5,000. Is that big or small? Like, I don't know. So it depends on the scale, right? But it's at least some measure of variability. And then we can take that sum of squares and we can divide it by, if we're working with samples, which we almost always are, the number of people in the sample minus 1, and this is going to give us our variance, right? We're just taking it, turning it into a new measure, metric of variability. It's just this one, this variance, a little bit more intuitive, or sort of a little bit more interpretable, not as interpretable as what can we do cited with that variance to get to something that's more interpretable.
Square it.
Take the square root of it, yeah. And what does that give us?
The standard deviation.
The standard deviation. And standard deviation is then nice because I can interpret that as the expected or the average difference of any randomly selected sample from the mean in terms of whatever units we're using to go through it and calculate stuff. Okay. All right, where are we? Okay. So when we're going through and we're calculating our ANOVA stuff, we've got our nice ANOVA table. This is going to be useful for organizing, calculating different statistics, looking at relationships between sort of some of the different figures that we're going to go through and calculate in our one-way ANOVA simple situation where we've got our between our treatment statistics, we've got our error treatments, then we've got our error statistics, and then we've got our total. We're going to calculate sums of squares, degrees of freedom, and mean squares, and then come up with an F statistic eventually. Okay. So let's go through, stop there, and come back. We'll start working through an actual sort of problem with that. So if you try and make sure that you've got the temperature example, that ANOVA handout that I gave you last time, because that'll help sort of work through some of this stuff. We ready to jump back into this? Cool. All right. So, gonna go through and do this, sort of walk through these by hand again. Although I will not say you'll never come up with not have the opportunity. I've actually calculated a one-way ANOVA by hand, sort of based on means and standard deviations, because I wanted to see omnibus differences across some stuff that they didn't do it. So you'll have the power to go through and do this by hand, sort of conceptual understanding, like the one time it happened. And then you'll be super excited about this, right? Like, when will I ever need this? Like, I don't know, like you'd be a bar trivia and something like, tell me what's the mean squared error, and then you'll know when you win heroes, right? You'll be the best in your bar trivia, right? All right, so notation. If we're talking about, and this differs, and this is probably part of what makes reading methodology literature difficult, is sort of notations vary widely, but for our purposes, we're going to use K as indicating the number of levels of a factor, right? Or this is just going to be our number of groups or conditions. Small n is going to be the number of scores within each condition. Big N for our calculation will be the total number of subjects. T is going to be the total, okay? Total sum of all scores within each condition is the treatment total. G is going to be your grand total, right? I have these in that handout there to try and help sort of keep your head square in terms of some of these different calculations. But if we go through and take a look at that handout, we'll see that I have simplified some stuff here. Sum of x squared, this is just going to be the sum of all your squared scores. So if you take 0 squared, 1 squared, 3 squared, 1 squared, 0, 4 squared, 3, go through, square all these, sum them all up, is going to be the sum of our scores. G is going to be the grand total. This is the sum of all of our scores, not the square total, but the sum of all. So the numeric, the sum of all of it. N going to be the total number of observations each we have. K is the number of level groups. Total sum of squares. This is the sum of squares for each group. Small n, the total number of scores within, and then mean is the mean of each group. So here, total, if we add these all up, gives us 5. If we take the sum of squares of these, it's going to give us 6. 5 people in each group, mean of 1. Same thing here, same thing here. Okay. You'll get a sort of general sense of where these numbers are coming from. Okay. So, again, wanting to note that anytime we're thinking about our ANOVA models, we're seeing variability across conditions down here, right? And again, variability within conditions, right? This is the effect that we're looking for. This stuff that's going on here, this is error. There are differences, we don't know why they're happening. The model is assuming that this is just random differences or individual differences, but a little bit more complicated than that, which is why we need to go through and make sure that we're clear on the methodology stuff. So, as we go through and start calculating things, we're going to kind of take one, so start with sum of squares total and work backwards. You don't have to do it this way, but just for the purposes of didactics, this is probably easier to think about this way. So if we're talking about our sum of squares total, what we're talking about is all the variability in the entire set of scores. So for all of our data, how many scores do we have here? What, 15 scores, right? Total variability in all the observations that we have. This is our total piece of the pie. This is what we're going to start partitioning variability in, or variance into, between and within. We go through, if we're looking at sort of the conceptual calculations or sort of by definition, what we've got here with our sum of squares total is the sum of the squared deviation scores of person I in group J from the grand mean. Okay? So what we've got here is our sum of our squared deviations of person I in group J from the grand mean. This is how far everybody is from the mean score of the whole entire sample. Okay. So if we're looking at, if we want to think about it as a distribution there, you've got the distribution of all scores across all groups, across everybody. You've got the grand mean. Your sum of scores total is a total variability in all the scores. Computationally, we can calculate this. Will take a while to go through and crank out that number. We can actually go through and take a shortcut. If we take the sum of our squared values and subtract the square of the grand total over the total number of scores. These are mathematically equivalent, so this is just a little bit quicker to go through and do. Okay. Again, thinking about this is all the variability in the sample. This is the total piece of the pie. This is what we're going to split into different components. Degrees of freedom for our sum squares total is going to be the total number of people we have in our sample, subtract 1. People see kind of where conceptually understand what our sum squares total is. So literally what we could do, if you wanted to calculate this, if in SPSS you just took all of the scores and ignored group and just ran the variance on that, or it would give you the sum squares total. Those would be functionally equivalent. Calculating for this example, if we go through and say sum squares total is the sum of our squared scores over square of the grand total over this samples, right? We're going to have 106 minus 30 squared over 15. Degrees of freedom, we got 15 scores in the samples, subtract 1. It's going to give us sum square total of 46 and degrees of freedom 14. Okay? So again, remember, the sum of squares is just a metric of variability. It's just telling us differences across all scores in the sample relative to the grand mean. People following up to this point? Okay. All right, so we got our total. What we're going to do now is we're going to go through and calculate our error. Okay. Our sum squares error is going to be, we're going to conceptualize this as the average amount of variability within each condition or group. Okay. This, by definition, is going to be the sum of the squared deviations of person I in group J subtracted from their sample mean, okay, or their group mean, right? So what I'm going to do is I'm going to take everybody in condition 1, subtract their score from that condition mean, square that, add it up, take everybody in condition 2, subtract their score from the mean of condition 2, add that up, take everybody in condition 3, subtract their score from their sample mean, square that, add it up. This is going to give me the sum of squares, my sum of squares error. So this is, think about this as the total This is just the variability, the combination, the combined variability across each one of my conditions. Okay. So again, I'm just taking all the scores within that cell, subtracting it from the mean of that cell, and pulling all those together. That's going to give me my sum of squares error. Computationally, I just calculate this as the sum of the sum of squares for each individual group. This is, again, we're thinking about this is just getting how much variability are we seeing within each one of these conditions. Okay. Again, variability here, groups, variability within groups due to individual differences. This is going to be your error term, part of your error term. We're going to, this is going to be important to sort of recognize, because there's a lot of things that you're going to go through. Can I pull for maybe some subsequent post hoc tests or things along those lines? Is this error term a good representation of total error variability across my set? Sometimes it will be, sometimes it won't. And so it's important to have a strong conceptual understanding of what's going on here. Okay. Degrees of freedom for my sum squares error. This is the total number of scores in my sample, like the whole sample, minus the number of levels of my factor. So we're looking at our ANOVA table. Sum of squares error, going to sum this up as the sum of my sum of squares for each group. Sum of squares of group 1 is 6, sum of squares of group 2 is 6, sum of squares of group 3 is 4. Add those up. Degrees of freedom, I got 15 people in my sample, 3 levels, 3 conditions. Goes through 16, my sum of squares error within the 16, degrees of freedom 12 here. All right. Last, we're going to work on my sum scores treatment. Remember, this is the variability or differences across my groups. Okay? And depending on whether or not we have a balanced or unbalanced design, start to calculate this a little bit different. In the case where we have, I need some of my deviations from my group mean, and subtract that from the grand mean, multiply that by the number of people in each cell. So in this case where we have a balanced design where we have 5 people, or 3 groups, 5 people in each group, what I would do is I would take the mean of group 1, subtract it from the grand mean, square it, the mean of group 2, subtract it from the grand mean, mean of group 3, subtract it from the grand mean, add up those squared values, and multiply that total sum by 5, either just 5 people in each one. That's going to give me my sum of scores treatment for my balanced design. For unequal sample sizes, then we have to weight those differently because I've got different amount of people in each group. Here, same thing, I'm going to take my group mean, subtract it from the grand mean, square that, multiply that by the number of people in that group, and then I'm going to take for group 2, the grand mean, or the group mean minus the grand mean, multiply that by the number of people in that group, right? So on and so forth, add those up for my unequal end. Because everything squares to 0 within our ANOVA table, if this is my sum of scores total, this is my total variability, right? And this is the sum of scores error. This is stuff that's just due to random variation within groups. If I take the sum of scores total, subtract the sum of scores error, what am I left with? Differences across groups, right? Again, sum of scores treatment, is variability after removing differences due to within group error. This is our effective interest, right, in addition to sort of whatever static else we've got in there. This is sum of scores treatment. This is the variability that we're looking for. And again, remember that when we're using ANOVA language, anytime we're talking about variability, we're talking about differences. Degrees of freedom here is going to be 1 less than the number of levels to our factor, so k minus 1. So sum of scores between, we take our sum of scores total, subtract our sum of scores within. We've got 46 minus 16 gives us 30. We've got 3 levels to our independent variables. Subtract 1 gives us our degrees of freedom between. We've got some scores here, degrees of freedom here. We've got that all set up. People see conceptually what we're talking about when we're talking about our treatment, our error total, so understanding kind of where these numbers are coming from and what they represent. Okay. So, we've got our sum of scores, right? We know that sum of scores is just a raw, unvarnished metric of variability, right? But what we're going to do is we're going to go through and take this and sort of translate these into something that's a little bit more meaningful, a little bit easier to work with. Because when our ANOVA model, remember our F statistic is looking at the variance, the ratio between treatment or between group variance to within group variance. And so when I'm talking about variability, I'm talking about sort of differences in general. Variance has a specific definition. Variance is a specific statistic. And what we want to do is we want to get at variances. And so within the context of ANOVA, variance is referred to as your mean square. Okay. But because mean square is just the same thing as variance, and we already know how to get variance from our sum of squares, all this kind of falls into place in stuff that we've done before, right? So remember that variance is just a sum of squares divided by degrees of freedom, because we've already gone through and calculated sum of squares, and we've already calculated degrees of freedom for everything. Once we've got that, then the mean square is variance is pretty easy to get. Mean squared for our group, for our treatment, is just going to be the sum of scores treatment over degrees of freedom treatment. Mean squared error, just the sum of scores error over degrees of freedom error. And this just gives us a variance component. So we can literally treat and interpret as variance just like we would interpret any other variance component here. So our mean square treatment, sum of scores treatment over degrees of freedom treatment, mean squared error, sum of scores error over degrees of freedom error, 30 divided by 2, 16 divided by 12, gives us our mean square treatment and our mean squares error here. And once we've got that, F statistic is pretty easy, right? F ratio is our test statistic. It's our mean squares treatment over our mean squared error. Oops. And so again, conceptually, and I can't emphasize how important this is to be thinking about sort of this F ratio in terms of our observed differences over the differences that we would expect under the null hypotheses. If what we're seeing in these data starts to far exceed what we would expect due to just random variability due to sampling error and things along these lines, what we're going to get is an F ratio that's starting to get larger and larger and larger. We're getting more and more likely to reject the null hypotheses here. So here, we've got 15 divided by 1.33 gives us an F statistic of 11.28. Questions about how we went through populating this ANOVA table, how we got sort of our different scores and put everything together here. Okay. So the nice thing about our ANOVA table, it's helpful, it's useful, everything, like I said, sums to 0. If I take my sum scores treatment, add my sum scores error, I get my total, and so you can go through, back translate any there. The sum squares for my degrees of freedom and my degrees of freedom error, it's going to equal the total. This gets my mean square, this gets my mean square, this divide, we get F. It all kind of fits together nicely. There's no independent cell in there that's not related to anything else. It kind of all falls in nicely. This is a nice way we can go through if we're doing hand calculations and check to make sure that what we've got makes sense, because if something here doesn't add up the way it's supposed to, you know that we've got something wrong. Okay. So again, what we've got here, our F test is going to be our variance between over our variance within. We got in here variance between and within. Our mean squared error, our mean squared treatment is just going to be sum squares treatment, degrees of freedom treatment, sum squares errors, our mean squared error, going to be sum squares with error over degrees of freedom error. So we go to start working this all out. Everything again fits nicely together, so it all squares up here. Okay, so people see how we go through and sort of calculate, at least in this simple example, how we got the things that we're trying to calculate. Any questions about ANOVA, how we're thinking about calculating it, or sort of interpreting any of the components? Okay, cool. So this is how we think about ANOVA from a classic standpoint. So as ANOVA developed, so this is sort of the sequence of calculations sort of developed around this means-based testing. But as we started to get more sophisticated in terms of our computations and sort of our statistical theory, we started to recognize that, well, ANOVA is fine. When we think about this as means-based statistics, it's different than other stuff. But when we actually look at the nitty-gritty at the math, ANOVA is just a special case of regression, right? There's nothing that we can do in an ANOVA model that we can't get from a regression model, right? And so this starts to really go through. We're going to put a much bigger emphasis on this when we get into next semester, talking about this approach to thinking about our means-based testing within the same framework as a general linear model, right? As we start to go in and getting more sophisticated types of analyses, right? Like some of the stuff Kyle was presenting, or some of the stuff that Ben and Sean do in terms of multi-level models and things like that. Even if we're using categorical variables and things like that, if we can fit it all within the context of this GLM framework, we can start to make connections and things start to make a lot more sense in terms of what we're trying to do. So if we're thinking about your grand mean here, right? Your grand mean is just the best guess without any additional information. So let's say, Alicia, I've got a group of 100 undergrads hanging out outside the door, right? And I said, they're out there, you can't see them. And I said, hey, I've randomly selected this undergraduate. Like in my head, like by the tail, right? They don't have tails, I didn't do that. But if I just said, I randomly selected this one undergraduate, I want you to tell me how much this person weighs, right? In the absence of any other information, what's your best guess? The average, right? And if I told you the average, maybe it's not undergraduates, maybe it's sort of, I randomly selected 100 people from the population of US citizens, right? And I told you the average weight of the population is 185 pounds. I told you I've got a randomly selected person from these United States. How much do they weigh? What's your best guess? 185 pounds. Are you going to be right?
Probably not.
Probably not. You're going to be off. But systematically, it's your best guess. You'll be less wrong if you guess 185 pounds every single time something comes down the pipe, right? And so again, this is just our grand mean. Absent any other information, my best guess is just the mean, right? But what we can start to do is we can start to put together a group model, right? And with this, what I'm going to do is, let's say, instead of just saying, oh, here's a person, and you just have to guess the population mean, now I'll tell you I've randomly selected a person, and then I'll tell you whether or not that person is either male or female, right? Now this is relevant information, right? And this is stuff that you can use to start adjusting your predictions about what this person likely weighs, right? And so if we're thinking about our group-based model, this is where we get into kind of like our ANOVA types of designs, right? So here, we've got the weight of person I in group J, right? And if I say, here is this person, they are a man, right? What you would do, your best case scenario in that case, is go through and take the population mean, right? And go through and add whatever the difference is between the population mean and men, right? So here, on average, men in the US weigh 200 pounds. I don't know, does this seem right? This seems high. This is what I found on health.com or something like that, but I don't know. But let's say it's true. Average male in the US weighs 200 pounds. The average of the population is 185. And so what I'm going to do is I'm going to take the population mean of 185, and I'm going to add sort of the group mean, subtract from the grand mean. That's 15, right? And so I'm going to say, well, this person then, functionally, I'm just predicting the group mean, right? Because if I take 185 and add 15, 185 plus sort of the difference between my group mean and the grand mean is just sort of giving me my group mean, right? So if I say, here's an average, I grabbed a randomly selected person from the US, they are male, what's your best guess? 200 pounds, right? Same thing, if I go through and I tell you I randomly select a woman, what we would do is we would take the grand mean, and we take the mean of women and subtract that from the population. That's going to give us negative 15. We're going to take the grand mean, subtract 15 there. Now we're back down to the group mean. So functionally what we're doing is we're predicting the group mean, sort of based on an adjustment. But from a model-based standpoint, what I've done is I've taken sort of the average for everybody, and then I've started to make an adjustment based on some individual difference characteristic. This, in this case, is being someone's sex, right? If it's a male, I increase my adjustment. If it's female, I decrease that adjustment. When we get into the final model, structural model, what we're doing here is we're just adding an error term. What we've got here is we've got the grand mean, right? Plus an adjustment for whether or not this person is male or female. And then adding on to that, the deviation from that person's individual weight relative to their group mean, right? And so if we go through and run this out, we've got the grand mean, the effective group, and then our error term is just stuff that we haven't accounted for here, right? This is just how much my weight differs from men's weight. That's going to be just how much you were off when, if I was the randomly selected person in this adjustment. That's sort of going into my error term. And so we can start to think about our ANOVA models. So this starts to look a lot more like a linear model, sort of like a regression model, and some stuff that we can start to do. It's not functionally different what we're doing in terms of section and variability. It's just kind of a different approach to get at the same type of thing. But this, as we start to get into next semester, gives us a lot more flexibility in terms of how we're thinking about these models. And particularly for you, one of the things we run into is we have violations of our underlying assumptions, and SPSS doesn't always do a great job of addressing some of that stuff. The package you're using will do sort of this better, but what it does is you start analyzing sort of ANOVA stuff within the context of sort of robust regression. It's actually pretty easy. It's giving you the same output as everything else, just using this type of approach as opposed to adjusting degrees of freedom and doing stuff like that. So as you start to get into more complex methods, it's sort of knowing and seeing the connections between these two starts to become useful. Don't worry about this a whole lot, but just kind of know it exists and is out there. Okay. Questions on this? Okay, cool. So, critical values for our F table, okay? F table, our F distribution looks like something like this. Lowest value here is 0. Chris, see why is on our F distribution, thinking about how we calculate our F statistic, why is the lowest value, minimum value of this 0?
I don't know.
Or asymptotically close
One.
to 0, right?
Wouldn't 1 make more sense?
Well, one, and so if we look at sort of where our sort of things are, we start to get there. But why can't we have negative F values?
So
How do we calculate F?
we do the systematic differences minus the random differences divided by the random differences.
Okay. And so what's the metric that we're using sort of in the numerator and the denominator?
Oh, variance.
Yeah, can variance be negative?
No.
It can't be, right? So the very minimum, and it can't actually be 0 either exactly. It can get infinitely close to 0, but,
Okay.
so what we've got is we've got a distribution that can't be negative, right? And so we're gonna stack it up on 0, but how large can our F values get?
Very.
Infinitely large, right? So we've got a different shape distribution that looks different than our t-test. Our t statistics can be negative, they can be positive, sort of in infinite direction. With our F statistic, we've got a different, sort of like a chi-square, right? Chi-squares can't be negative, right? And so we've got a different distribution that has a right skew, and the right skew depends on the degrees of freedom of the specific distribution. So again, because we're looking at a ratio of 2 variances, our F values are always going to be positive when the null hypothesis is accurate, right? We're going to go through, or reasonable, we're going to get values close to 1. But like our T distribution, the specific shape of the F distribution we're going to be looking at is going to depend on degrees of freedom. And this time we're going to have two degrees of freedom. We're going to have degrees of freedom in the numerator, degrees of freedom in the denominator. Remember that T is a family of curves. Same thing F. F is the same family of curves. And so if you take your F table that we sort of passed around last time, you'll see again here it's set up a little bit differently. So we've got great tools now for actually getting more precise values, but old school we were using tables. And so we go through, and in this case, what do we get? Here we had, in our example, 2 degrees of freedom in the numerator, 12 degrees of freedom in the denominator. And so if I go through and I'm looking at the table that is alpha 0.05, it's the first one. If you go to the second page, it's alpha 0.025, third page, alpha 0.01. Right? So if we look at 0.05, and we say, we find we have 2 degrees of freedom in the numerator and 12 degrees of freedom in the denominator. We find a critical value for this F statistic with 2 and 12 degrees of freedom of 3.89. We'll see where we got that. Okay. And if we wanted to look at critical value for alpha equal 0.01, we just go to the 0.01 table, right? Go through, take a look, 2 degrees of freedom, 12, we get 6.93. Tells us where that is there too. All right. Who doesn't have an F table? You don't have, you guys don't. You have an F table. Okay, over here. Do you guys have F table? Okay, good. We're gonna do a magic trick here in a moment. Right? Turns out the T and F hold a direct relation with one another. If we're talking about the F curve with 1 degree of freedom in the numerator. If I've got 1 degree of freedom in the numerator, what does that tell me about the number of groups that I'm comparing? Yeah, it's 2, right? If I've got 1 degree of freedom in my numerator, I'm comparing 2 groups. And what else can I use to compare 2 groups? A t-test, right? And so what we find, for F tests with 1 degree of freedom in the numerator, F is equal to the square root of T, right? So if I take a look and find a critical value for F with 1 degree of freedom in the numerator, and look at the same degree of freedom, t with the same degrees of freedom in the denominator, and I take those are mathematically, Chris M, go through and find f value for critical value for 1 degree of freedom in the numerator, 20 in the denominator, with alpha equal 0.05. Tell me what that is.
I got 4.35.
4.35. Okay. Is that right? Okay. Someone, does anybody have a T table on?
I have a T table.
You got it. All right.
I thought it was the F table.
All right. Good. Okay. Chrissy, tell me, find a two-tailed t-test at alpha 0.05 with degrees of freedom 20.
Okay. 2.086.
2.086. Okay. So if we go through and I take 2.086 and square it, what do we get? Yeah. If I take 4.35, I square that. Right. This is helpful to know. Sometimes what you'll see when we're running, and has anybody seen this? Running through and looking at, running into a paper where people are running like t-tests or pairwise comparisons and reporting F values. Have you seen that before? Okay. Kind of weird, kind of funky, right? Like, oh, why don't you just give me t values? Well, depending on what type of thing they're doing, sort of, who knows, right? And sometimes we want to know t values because t values are easy for me to interpret than f values. I know what's a big t value, what's not a big t value. And sometimes if it's a paired sample test and they didn't provide a degree of freedom, if I have a t statistic, I can calculate an effect size for that. Recognizing this allows you to go back and forth and sort of work back and forth between this stuff. Okay. Yeah. Okay. Questions about relation between T and F and how to go through it and move back and forth between those. Z also is related to chi-square. If you take a Z, and square a Z value, I think that turns it into a chi-square value within 200 degrees of freedom, I think. Pretty sure. I'll look into that. Something I learned at one point in my first year of graduate school. So like, there's like one random piece of useless information from this entire class that you'll remember. So who knows? We'll take bets on what that's going to be. All right. So conclusion and interpretation for this. So our hypothesis here is that mean performance in condition of 50 degrees, 70 degrees, 90 degrees, all going to be equal. Our alternate hypotheses, mean learning scores will differ in at least one temperature condition. I'm going to mark myself off right there, and I'll have a little thing that says pop, and I might highlight it. So put that in. We'd say across hypothetical individuals completing tests in sort of 50, 70, 90 degrees, we'll see at least one difference somewhere in there, right? So at least sort of something to go through and let me know that we're understanding that we're trying to infer something about the general population. And for the omnibus test, with what we've done here, pretty straightforward, right? We're going to say F value of 11.28 falls within critical region set by alpha 0.05 for F critical 2 and 12. Results provide support for potential effect of ambient room temperature on learning the larger student population. Given the data, we're largely incompatible with the null hypothesis of equal performance across conditions. Then we go through and calculate our p-value, s-value, Bayes factor. So it's all actually, even though we've got 5 people, the difference is quite large, right? And so these data, so our p-value here is suggesting that these data are generally not compatible with this null hypothesis, right? It's saying that if we look at our s-value, again, thinking about s as evidence against the null hypothesis, right? So this being our s-value of 9, so these data providing similar evidence against the null hypothesis of equal performance across these conditions, as would be getting 9 consecutive heads in a hypothesized fair coin, right? So again, when we're talking about s values, remember, I think we're, it's not when we're talking about s values, thinking about this as a continuous measure of evidence against the null hypotheses. Some people have gotten turned around and sort of want to say that the likelihood of sort of this difference between these things and sort of assuming the null hypothesis is true, that's too much. It's just saying all this is saying, and again, you can cut and paste the same thing every time. Hopefully, if you're just cutting and pasting it enough, it'll sort of internalize it. So to say these data are providing similar evidence against the null hypotheses, as would be sort of finding this many flips, consecutive heads in a hypothesized fair coin. 9, I don't know, I'm sort of starting to really question whether or not, Nick, you're flipping a fair coin if you call them 9 heads straight in a row, right? It's not overwhelming, I'm not saying it's impossible, but it's incredibly unlikely, right? Same thing with our base factor. I would say, again, remember here where people are getting sort of tied up, remember that our base factor are talking about the odds of the null, or the odds of the alternate hypotheses versus the odds of the null hypotheses. And this is a very specific thing. Whereas odds are a different thing. We have to be careful. We can't treat odds like they're probabilities because they're different, as we went through and talked about before, right? So we can say, we could say the likelihood of the alternate hypotheses of non-equal performance is approximately 33 times that of equal performance, right? Here we're talking about likelihood. We can use that kind of interchangeably with odds, where we can say the odds of based on these data, we'd suggest that the upper limit of the odds for not different performance across these groups is about 33 times that of the odds of equal performance. We would say that there is a about a 3,200% increase in the odds of the alternate relative to the null, if we wanted to sort of use this as percentages. So there's different ways to go through and describe this. You just want to be sure that you're being precise in how you're talking about your S values and your base factor. Also, when we're going through and writing these up in your write-ups, don't feel compelled to try and force S values and base factors into there if it doesn't make sense to you. If it does, use them, that's awesome. If it doesn't, don't have to worry about it. That's why I have a question on there to sort of give it to me, give me an interpretation so that you know what it's talking about, and then you can go through and try and work it in if you want, right? So, I mean, where I'm thinking that this is sort of kind of helpful is if I've got a marginal effect, something that's like 0.04 or something, and I can say, well, this is sort of functionally equivalent of getting 4 consecutive heads in a hypothesized fair coin. That sort of puts that strength of evidence against the null hypotheses into some perspective, right? Or I say that based on these data, upper limit of the odds of the null or the alternate relative to the null is like 3 times as great as sort of the odds of the null hypotheses, right? So it starts to put that into some context that that's actually not a super strong effect, right? Or if it's super large, right? And this is where if you want to use scientific notation to report your p-values, go nuts, because again, those are 2 different strengths of evidence, right? And if we truncate everything to p less than equal to 0.001, we lose a lot of information with that, right? So if you really have an effect, you've got a test statistic of like 12 or something like that, and it's the p-values, p is equal to 2.3 times 10 to the negative 10th or something like that. Calculate, I mean, that's not easy to sort of think about. You calculate an S value and a base factor there, right? Base factor, basically the likelihood of the alternate hypothesis is 1 billion times greater than the odds of the null. So it's saying that these data functionally can't exist if the null hypotheses were true, right? And so just using this flexibly to try and communicate whatever conclusion that you're trying to put together, but don't try and feel like you have to force these into your interpretations, okay? Questions about this? Yes.
So since we can't really tell what thing is different in an ANOVA, we don't have to, so like our interpretation of the entire test would be that it's likely that there is some difference.
Yeah,
We
at
just
this
don't know.
stage of the game. And with the knowledge that you're equipped with right now, that's as far as we can go.
Okay.
Okay, and then and then the hard part gets into how do we start unpacking this? What's our approach to go through and do this? And this is why it's hard. And this is why for applied statistics, if I got 10 different ways I can go through and approach it, I got to know what my options are, what the strengths and weaknesses of those things are, and how to best go through and tackle this. It's tricky in one way. I know as soon as we get into factorial designs, it can turn into a free-for-all, so you just want to make sure that you have a good plan on how to move forward with stuff. All right, cool. Oh yeah, also too, in terms of Bayes factor, right, so if you want to use, so remember we provided these in terms of sort of strength of evidence. Here, with a Bayes factor of 33, it's qualifying that as fairly strong evidence against the null hypotheses, right? Or fairly strong evidence of the alternate relative to the null hypothesis. Remember that S value and your Bayes factor are giving you slightly different information. S value is giving you evidence against the null. So we're not talking about alternative hypotheses, just evidence against the null. Bayes factor is kind of interesting in that it's sort of actually giving you database odds at the upper limit of the odds of the alternate hypotheses versus the odds of the null, which sort of starts to get to much more at what we'd like to be doing, sort of testing within the context of our statistical tests. So just make sure that you're squared away. But these start to give some relatively common benchmarks for general strength of evidence based on your Bayes factor. Okay, so I want to talk about effect sizes. When we get into ANOVA designs, Alicia, can we start talking about standard deviation and differences across groups? If we're looking at paired samples, but what if we want to get to everybody? It starts to become difficult, right? Because standard deviation differences, that difference assumes two different, a pairwise comparison, right? In this example, we've got more than 2 groups, right? We've got 3 groups, and we have 4 groups or 5 groups. Hopefully you might get more than 5 groups in one way ANOVA at any point in time, but it's technically possible, right? And so what we want to do is have some way of quantifying the magnitude of the effect in something that is easily communicated along these lines. And so we switch over to, instead of pairwise effect sizes, right? What we've got into is measures of association, okay? In measure of association, we most commonly see for one-way ANOVA is going to be eta squared, okay? Eta squared is going to give us a proportion of total variability in our outcome that we can attribute to whatever our grouping factor is, okay? So if our for this example that we went through, let's just say that our eta squared was 0.15. Okay? We would say eta squared is equals 0.15, and how we might, the practical interpretation we would put on that, we would say, based on these data, temperature condition accounts for approximately 15% of the total variability in our outcome, right? What does this sound like? For anybody who has a regression background.
Yeah, we can't hear
We're within a regression, we're talking about proportion of variability. Yeah, what is it?
Is it R squared?
Yeah, it's an R squared. Eta squared is just R squared for an ANOVA model. It's the exact same thing, right? Stata will give this to you. This is sort of right there in the output. It'll give you an R squared for the model in ANOVA. That's just your eta squared, is all that is, right? So it's a measure of association. But this is what makes effect sizes hard, and I think this is what has been a barrier to sort of mass adoption and regular incorporation, is because depending on the analyses we're using, the effect size, the appropriate effect size changes, right? It doesn't make sense to talk about a D in terms of an overall ANOVA model, because D doesn't mean anything in an omnibus ANOVA effect, right? It's not a standard deviation unit difference. I can take it and turn it into a D, which doesn't make any sense, right? But for our ANOVA model, again, if we're taking this GLM type of approach, if we're thinking about our omnibus test telling us the relationship between our categorical grouping variable and our continuous outcome, we can think about eta squared as telling us the proportion of variability in our outcome that is at least shared with our grouping variable, okay? Judd and McClellan often will also say that we can interpret eta squared as the percent reduction in error, or the PRE. And this is kind of interesting, right? So we're thinking about eta squared is giving us the level at which error in prediction has been reduced by considering our group, right? So how much error in our model is decreased by having grouping factor in there? Well, if our eta squared is 0.15, we'd say we've got a 15% reduction in error based on the inclusion of this, right? So it's just kind of the inverse of thinking about proportion of variability accounted for, proportion of error reduced. Now, so the problem is, eta squared is common. Eta squared is pretty easy to calculate, right? We just take our sum of squares treatment divided by our sum of squares total. And if we look at eta squared, the interpretation starts to make sense, right? Haley, or Siley, sorry, you're not Haley. Siley, what does the sum of squares total represent in our ANOVA model?
The total with like the standard.
Yeah, but not quite the standard error, but the total variability in our data, right? All the variability that we have to account for. And what's our sum of squares treatment represent?
Just specifically between the groups.
Right. And so if we take how much we're accounting for in terms of our effect over the total amount of variability that we have, it starts to make sense that this is sort of of the total, this is the percentage that's attributable to our grouping factor, right? Now the problem is this is easy to calculate, super common, but what ends up happening is we know that eta squared is positively biased, okay? And if we consider what's going on here, if my null hypothesis is true, okay, there truly is no differences across each one of these populations from which I'm drawing the sample. Alicia, are my sample means all going to be the same? If there's no difference in the population, are my observed samples all going to have exactly the same mean?
They should, if it's all the same.
Well, the population is the same, but is my sample always going to equal exactly my population mean? No. So are all my sample means going to be the same? No. And so there's going to be some variability, right? There's going to be some differences, right? But eta squared can't be negative, right? So we're always going to have, our sum of squares treatment is never going to be 0. It's always going to be some number that's greater than 0, right? And so what happens is the calculation, this is always going to be positively biased. It's always going to capture, because remember, our eta squared is capturing not just the systematic effect of condition or treatment, it's also capturing sort of just, it's capitalizing on some just random type of error. So think about, even if a case where the null hypothesis is exactly true, my eta squared is still going to be some positive value, right? Which suggests it's biased, right? On average, eta squared is never going to be equal to the actual population parameter. It's always going to be a little bit above. And so what we go through and we can calculate instead is a correction for this we call omega squared, okay? Omega squared is a better test statistic because we think about omega squared as a population-based statistic, okay? Eta squared is a nice descriptive statistic in that it tells us in these data, in the data that I'm looking at right here, the proportion of variability, of total variability in my outcome that's shared with my grouping variable, okay? But in terms of using this as an estimate of the actual true population effect, it's going to be too big, right? So what we get with omega squared is a downward correction, gives us a more reasonable estimate of the actual population effect that we're probably interested in, right? Now, some limitations here Omega squared is still positively biased to some extent, but much less so than eta squared. So it's still not perfect, but it's better than eta squared. Also, the assumption of omega squared assumes balanced design. We start to become concerned about whether or not it makes sense to calculate omega squared, right? Calculation, at least for our one-way ANOVA, isn't terribly difficult, but it's a little bit more involved than this. Here we're taking our sum of squares treatment minus the number of levels of our grouping variable minus 1 times our mean squared error over sum of squares total plus mean squared error. This gives us our omega squared, right? This starts to get more and more complicated as we get more and more complex designs. One of the sort of drawbacks of this is depending on sort of how you actually set up your design changes how we calculate omega squared. But in general, a better estimate of population parameter or the population effect than eta squared is going to be. Yeah.
Is omega squared also calculating the percentage reduction in error?
Yeah, thank you. Yeah, we would interpret it the same. The only thing that I would change in terms of the interpretation of omega squared, I would just sort of identify this specifically as a population statistic, right?
Okay.
So, we would say based on the data we collected, based on omega squared, we would expect temperature condition to account for approximately 12% of the total variability of performance in the hypothetical population of individuals completing this task or something like that, right? Whereas eta squared much more for these data. Questions about eta squared, omega squared. We can also get eta squared based on test statistics. Again, if you're doing it, just use this. This is going to be more precise. But if someone gives us degrees of freedom in F test, I can use that F as long as I know degrees of freedom and go back through and back translate and get an eta squared off of that. Other effect size that's used for one-way ANOVA, and this is going to be important for power calculations, is F. Okay. Now F is what G power, if we're trying to calculate effect size for ANOVA, it may ask for F here. F is a direct function of eta squared, so one or the other. Problem is that F just doesn't have a good sort of conceptual interpretation to it, right? Or at least not one that I can derive from. So know about F as an alternate measure of effect. It just, I prefer eta squared omega squared because proportion of variability. I mean, I can tell you that and you kind of get a general sense for kind of what that means, right? So interpretive standards based on Cohen for eta squared omega squared, small, medium, and large, right? So it's the small end, we're counting for 1% of the variability and the total variability in our outcome, right? So not very big, but medium, large. By the time we get up to 14% of the variance, we're talking about a fairly large effect. Interpretive standards for F. So again, you can take those, turn those into those. But this is just if we're running power calculations and we want to say we're assuming a medium effect or a small effect. So this is what we're going to go on there. Questions about effect sizes here? And this again is why how it starts to get complicated and confusing, because you're like, okay, now I'm doing this, and so what effect size do I use? How do I interpret things along back and forth? Keep omega squared separate, right? So this is eta squared, so we're going to do it. I don't know what the relation is between F and omega squared. So if you want to calculate F, try to keep it sort of same here, so this being sort of kind of its own separate population effect. And, calculation of confidence interval around eta squared. Pretty straightforward. What we do is we just go through in our non-centrality calculator here. Has anybody pulled this up yet and used this at all? Okay. You'll need to do this for this next set. So, and I talked with Angela, who's a big Mac user, on how she did that, and apparently she had to go through and hook in with the lab in terms of using the online calculator to be able to go through and run this on a Mac. But Mac users who show hands. Okay, so everybody except for Chris and Sally. Okay. As soon as one of you figures out how to go through and do that, please share that with the other people. So, or if you find a tool that is compatible with your computer that sort of gives you the same thing, cool, use that. But for right now, I know that this works and this is accurate. So just pull this up from the last thing. I think are you guys already like linking it remotely to this lab to go through and use some stuff? Okay, so if you're doing that, you should be able to get online and just pull up this tool and be able to use it. It shouldn't be too big of a deal, but just make sure you're able to do that. We'll pull up this non-centrality calculator here, putting in an F dish. So let's say we want non-centrality parameters around our F test. Punch in your F value, numerator and denominator degrees of freedom. The thing to remember here is what we want to do when we're calculating confidence intervals around eta squared is we want to go through and we want to request a 90% confidence interval as opposed to our standard 95. Any ideas as to why we're asking for a 90% confidence interval as opposed to a 95% confidence interval? Can I get a negative omega or eta squared? I can't, right? And so this is the same thing when we talked about confidence intervals around one-tailed tests, calculating 90% confidence intervals around one-tailed tests, because we can't. So we're just looking in one direction, right? And if our alpha is 0.05 for a 95% confidence interval, at alpha 0.05 for a two-tailed test, we got 2.5% in this tail, 2.5% in that tail, right? But with the one-tailed test, we don't have sort of negative values. It's all sort of one thing, right? And so what we'll do, because eta squared can't take on negative values, what we're going to do for eta squared is calculate 90% confidence intervals as opposed to 95% confidence intervals. So make sure your 90% confidence interval here is checked. Hit compute. This is going to give your upper and lower non-centrality parameter, or your upper and lower limit for your non-centrality parameter. And then it's easy. Just take your lower divided by your lower plus n. That's going to give you your lower limit for eta squared. Upper divided by upper plus the number of total people you have in a study. Times that by, divide that out. That's going to give your upper. Then you got upper and lower level confidence intervals for your effect sizes there. So pretty easy, straightforward, simple. But if you're going to calculate confidence parameters around your effect size, remember that this is for eta squared and not omega squared, so make some adjustments there. I mean, omega squared will still fall within the bounds of this limit. It just technically won't be the right one because it's using a separate estimation. All right. So assumptions of our ANOVA models, not too different. It's basically an extension of our ANOVA, right? Extension of our t-test, because t-test is just a special case of ANOVA, right? If I have two groups and I run a one-way ANOVA with two groups, it boils down to a t-test. It's sort of the same. It's mathematically equivalent, right? And so because of that, our assumptions are largely the same here. We have homogeneity of variance assumption. We're assuming that the variance in population 1 is equal to variance in population 2, 3, 4, so on and so forth. Okay. When we get into a regression model, we can start talking about this assumption is homoscedasticity, but we just generally talk about it now as homogeneity of variance. Okay. Other thing too, so with this foreshadowing and thinking as we move forward, remember, so our table here, right? If this is the mean of my group, any deviation I get from the average of my group is what?
Error.
Error, thank you, right? And so because of that, right, if we're saying that we have equal variances across my groups, basically what I'm saying is that there are equal error variances across my groups. And so helps starting to think about kind of what that's meaning here. If we have violations of homogeneity variance, we can talk about this as heteroscedastic errors. It's a term more common in regression models, but functionally it's talking about the same thing. Okay. We have normality assumptions. We are assuming here, remember that there's no normality assumption for the actual observed scores. We're assuming normal distribution of the sample means, right? And so under what two conditions does the distribution of my sample means start to become normal? What is it?
The population.
Population is normal, and what else? Yeah, I have reasonably large samples, right? So they're around 30-ish, yeah, you know, kind of about there, right? So even if my observed distribution in my data looks kind of wonky, as long as I have reasonable size samples or am confident that the population for which I'm drawing has a normal distribution, I'm sort of pretty much okay with this stuff, okay? But again, because this distribution here, everything that we're talking about in terms of lining up, if my grouping factor accounts for 100% of the outcome, then everything, I shouldn't have a distribution. It should be all, everybody should be all on the same page. But because I don't, I have different scores. I can think about the differences in these scores as errors, and so I can also think about, too, in terms of when we get to regression, thinking about this as normal distribution of errors. Because anything that's not, any value that's not falling exactly on the mean represents error in this distribution. Okay. We assume independence. We are assuming here that tomorrow's score is not influenced by Siley's score, is not influenced by Chris' score. Everybody's independent of one another, but we don't have common influence. And then informally, we're expecting not to have outliers and having relatively equal sample sizes across groups. As we start to split that up, as we start to get unbalanced designs that are super discrepant, it starts to cause some problems in the underlying mathematical theory. We can go through and make some adjustments, but it's never as good as just having sort of relatively balanced designs in the first place. All right. People comfortable with our assumptions? Sort of not anything super new here. Okay. Impact. All right, and this starts to become important when you're going through your screenings, right? Wanting to, based on sort of your diagnostics for what you're seeing in these data, not only being able to, not only saying, hey, there's a violation of homogeneity or variance, and that's no good, right? Being able to start to predict exactly what the likely consequence of that is going to be. What we know is just like our t-tests, all of our means-based tests are fairly robust to sort of single violations of sort of the underlying assumptions, right? So if I've got data that are very much not normal, right? I've got some weird stuff going on. My results are fairly robust to this, okay? So in my dissertation, I had some doing means-based analyses on some scores that were pretty skewed. But again, because my cell sizes were pretty large, about 50-ish, right? And because the underlying assumption involved the distribution of the sample means, even though those scores were skewed, and I expected them to be skewed in the population, it made sense that they were skewed, still because I had a reasonably large cell size, those analyses were robust to violations of normality here, right? I can also have violations of homogeneity and variance, assuming distributions have similar shape and the largest ratio, the ratio of the largest to smallest ratio doesn't exceed 4.1. Right, so if I've got relatively, even if my distributions aren't great, right, they're kind of skewed, but as long as they're kind of skewed in the same direction and the ratio of the variance in the largest variance group to the smallest variance group isn't sort of more than around 4 to 1, we're still probably going to be fairly robust to some of this stuff. Okay? Where we don't get robust, same thing with our t-test, if we start doubling down on violations. If I have any violation of independence, with group-based designs, when do I have violations of independence? Anybody know? Yeah, go for it. Tomorrow.
If like you're looking at comorbidities, for example, and you have like ADHD only, ASD and ADHD, or
maybe, but still, what we're doing in that is we're still assessing. So I have Doug, right? And I assess Doug, and I'm assuming that Doug's responses and things like that are sort of independent of sort of Bill's who I have coming in next, right? Where do we start to have problems with independence?
I can only think of just one example, but I know that if you're looking at like couples,
Yeah.
you can't especially like if you're looking at something like couple satisfaction, those are probably pretty dependent on the other person.
Yeah.
So you can't parse those apart.
Yeah. And this is where we start, if we're looking at something that's dependent not on other things I'm measuring in that person, but if I'm measuring something that's dependent on other people. And so if we have certain types of data, so dyads are a big one, right? I can't just take a bunch of men and women and throw them in together and then just treat them all as if their ratings of satisfaction were independent of one another, because they're not, right? Same type of thing if I have, let's say, a school-based intervention for ADHD or something like that, right? Or some learning intervention I go through, and I have kids in this classroom get the intervention and kids in this other classroom don't, and so I sort of section things up by classroom. Well, kids in that individual classroom, they're all in a common environment with the same teacher, and so kids in that classroom, their scores are more likely to have at least some relation with one another, as opposed to a kid from this classroom and another kid from the classroom, a different classroom that got the same intervention, but they're less likely to be everybody in the same classroom. So we're talking about some nested structure in terms of data, right? Because they've got the same teachers who are doing it at the same time, so there's individual differences there. And so when we start to see that nested structure of data, dyads, sort of grouping and stuff like that, we start to have problems with ANOVAs. Basically what happens is our test is too literal, right? Like we're not taking into account the nested structure, which makes there's dependency that we're not accounting for, which makes our standard errors too small. And if our standard errors are too small, what does this do to my test statistics, CJ?
Increases.
Yeah, it makes them too big, right? And so I'm more likely to claim effects when I shouldn't be claiming effects if I'm not accounting for this nested structure. I was just actually working on a paper with this where we had trying to run some analyses for group treatment for PTSD, right? And looking at individual change within group treatment for PTSD. So you have measures, longitudinal measures nested within individuals. But those individuals are nested within groups, right? And so the idea that sort of all of us are in a cohort and all of you guys are in a cohort, that my treatment trajectories may be sort of more, there may be some dependencies in here relative to what you've got going on. So we have to try and understand sort of the potential impact of that nesting and things like that. And if we don't, we start to get biased results. So if we have anything like that, we need to be either looking at a multi-level model or something along those lines, but more consistent with the types of things that we're doing. If we have evidence of different shape and unequal variance, okay? So if I have samples are suggesting the relevant populations are very different in terms of the variability, and so these samples are suggesting very different shape, then that starts to become problematic, right? If my condition A has a strong negative skew, my condition B has a strong positive skew, and those variability is different across those two groups, then that starts to become a problem, right? If I have unequal variance and unequal sample size, okay, that's a problem. This is probably the one that's going to come up the most, right? What happens if my group with far more people has the larger variance? What am I concerned is going to happen?
It's going to impact the total variance.
Yeah, is it going to, so I've got a group of 20 people and a group of 100 people, and the group with 100 people has 5 times the variability that the people with 5 people. What am I afraid is going to happen to my overall estimate of variance?
That it will be increased.
Yeah, it's going to be too high, right? Because it's biased towards the group that I've got a whole bunch of people in there, right? What if my small group has greater variance and my group with 100 has less? Then I'm concerned that I'm underestimating the variance, right? Because I get one mean squared error. My mean squared error is capturing the within group variability for the whole design, right? But if I've got different groups with different sizes with very different variances, what does this do, CJ, to my sort of confidence that this mean squared error term does a good job of getting, on average, the within group variability?
Decreases your confidence.
It decreases the confidence, right? And this starts to become problematic for a lot of our post hoc analyses and our contrast analyses. We're sort of capitalize on the strength of the design and pull that mean squared error. If that mean squared error isn't any good, then we start to have concerns about whether or not that's something we should be doing, okay? And then violations of normality in small samples. I've got 15 people in my sample and got really, really wacky distributions, then that starts to become problematic, right? So if we go through and we do find that we have some violations, one of the things that we can do, if we have cases involving unequal variance, unequal sample size, we have a Welch procedure. We can request this in SPSS and data. It'll give us an adjusted test that provides a correction to the F value and the degrees of freedom to account for differences in variability and differences. It's a big emphasis on this, and I think it's really smart. This doesn't make this correction, because we have a corrected statistic, doesn't mean that it fixes it. It's not like your variability, differences in variability goes away. If I'm finding that I have very large discrepancies in variability within condition variability, I should be looking at that and trying to understand why, right? Particularly if I'm running an experimental design, right? I've got condition 1, condition 2, and condition 3, and they're all doing different stuff, but variability in condition 1 is wildly different. I got people all over the map versus condition 2, people are all kind of in the same spot, right? That suggests that there's something going on probably that may be meaningful for understanding the thing that I'm trying to understand. Just because we have corrected tests, we shouldn't just say, oh, well, we're just going to use our corrected test and sort of move forward and just kind of ignore what's going on. If we're seeing large discrepancies in the variability that we're seeing within sort of different groups that we're trying to compare, that should be keying us into sort of thinking about what could be accounting for this different variability, what's going on in terms of the phenomena of interest that starts to sort of contribute to some of these differences that we're seeing. Okay. Questions? All right, cool. So let's finish off. We'll finish off today. So we're working through some screening stuff. If you got your handouts for your screening, so for this one-way ANOVA data. And so what these are, some hypothetical data. And so the idea is that we're going to say that because in the larger literature, so when we look at social science literature, that we have see this effect where people from similar groups tend to be better at identifying, maybe more responsive to other members who look similar to or like them than we see responsive to other dissimilar targets, right? And so because of this general thing, we've got a group of investigators that are interested in the extent to which individuals with different racial ethnic backgrounds might start to respond differently to different types of emotion primes containing sort of homogeneous actors of sort of a homogeneous identity, right? So if we go through thinking about studies that are manipulating affect or things along these lines, right? Generally what we see is a group of slides or pictures or films containing predominantly sort of white non-Hispanic actors, right? And this is what we go through and we use for everybody. But it's possible that maybe this film doesn't elicit the same type of response or consistently the more safe type of response in white majority individuals versus individuals from more diverse backgrounds, right? And so what we've decided to do here is we take a diverse group of undergraduates and we're asked them to provide ratings of emotional valence and emotional arousal in response to a humor eliciting film that features white non-Hispanic actors, right? We're just, again, this is an important question, right? If we're going to use this as an affect manipulation, it's probably important to know that this is doing the same thing across individuals, irrespective of sort of being able to identify based on similar to dissimilar backgrounds. So we're going to state the null. We're going to report the null using statistical notation, our hypotheses test, calculate an effect size, S value, base factor, and then go through and summarize everything together. Okay? What we're going to do first, we're going to jump into screening. Okay? So you pull up your data set and take a look. Okay? So what we have here is we have participant number, and then we have a code for racial ethnic background, and then we have ratings 0 to 8 of valence and ratings 0 to 8 of arousal. So despite the best intentions of our approach, when we're trying to create a categorical variable of racial ethnic background, what we've ended up doing is we've got white non-Hispanic individuals, we've got a good number of those, we've got black non-Hispanic individuals, we've got a good number of those, and then we kind of fell apart in terms of getting sort of cohesive groups. And so what we've done for the purposes of this example is then kind of lumped everybody into an other minority category, right? Which is not a useful way to go about this. For the purposes of this example, it gives us something to sort of go through and look at. But if we see research like this, the first thing we should be doing is saying, okay, well, you can't just group everybody who's not white or black and assume that they're all going to respond the same way. Particularly if the whole purpose of this study is to go through and look at racial ethnic differences and responding against like or different folks. But we'll set that on the back burner for right now and just go through and start to take a look, but it does sort of complicate things in terms of interpretive stuff. But if we're pretending that these are good groups, we've got 3 different groups. And so the first thing we want to do is, probably what I'll do is go data, analyze, descriptives, and then I'm going to go through and take a look at valence and arousal. I'm just going to paste this in real quick. And so what I'm doing here is I'm just going to use this to get a quick sense for accuracy and plausibility. Okay. So going through and running this, I can see for valence, I've got values ranging from 1 to 8. For arousal, I've got values ranging from 0 to 8. So that all looks good. All my values are in bounds, right? I've got 99 observations for valence, 99 observations for arousal. If I go through and I take a look at my data set, I got 99 people in the sample, right? So number one thing, do I have any missing data? No missing data, so that's good. Are all my values within range? Yep, they are, right? So doing a quick check here. Now in SPSS, one thing I could do, you can do this in Stata, you just hit sort and sort of type in whatever. But I could go through and I could sort this, and any value that's missing is going to come right to the top, right? And so I see I don't have any missing values here, no missing values here, no missing values here. So that's just a different way I can go through and assess and see whether or not I have any missing scores in the data. But want to go through and make sure that we've got everybody, that we're not missing any scores, and everything's in balance. So we can go through and check those 2 boxes off. So now what I'm going to do is I want to go through and take a look at differences or my distributions of scores within each one of my groups. So what's the first thing I have to do? Nick?
Split file.
I have to split my file. Why do I have to split my file?
Because we want to look at the group, so you want to tell the program to separate your output by groups.
Yep. I'm going to tell SPSS to go through and until I turn that split file off, I want it to be doing everything separately across my different groups, right? And this starts to become particularly important for calculating your standardized scores, right? Because if I don't split the file, and then if I just go through and run standardized scores without splitting the file, it's going to run z-scores based on the grand total, the grand mean of everybody, and I don't want it to do that. I want to be looking at mean scores for my individual groups. So I'm going to go through and I'm going to go to data, split file, and split file by ethnicity. I'm going to say compare groups. I'm going to paste that into my syntax file up here. And then I'm going to go back to analyze descriptives, and descriptives. And this time I'm going to save standardized values as variables. You go to options, I'm going to ask for skew and kurtosis. I'm going to hit continue here and paste. Okay. And again, remember you can go through, label your syntax files so you can remember everything that you're doing. But I'm going to go through, highlight all of that, and I'm going to run it. Okay. And if things have done what it should be doing, we should see my different groups be sectioned off into different categories here. Okay. And so, based on this output, Chris, am I seeing, is there anything of interest in terms of my distributions for valence or arousal across any of my 3 groups?
No, the primary thing is just your group sizes are completely off, like one's double assessed another, but in terms of the actual values themselves, they don't seem clear.
Okay, what's maybe one value in terms of my distribution that might be sort of a little bit, that might catch my eye?
Someone squared a 0 in the black mountain span.
Oh, okay, yeah. If I'm thinking about skew kurtosis values,
Alright.
distributions.
The kurtosis for white non-Hispanics is 2.
Yeah, so it's a little high, right? So I think based on this table, this is kind of what I'm taking off of this. You're right, sort of noticing that we do have an unbalanced design, right? We've got twice as many people in my white non-Hispanic group than sort of my heterogeneous other group. Now, a 2-to-1 difference in terms of unbalanced, it's an unbalanced, right? It's probably not the worst thing that could ever happen in the universe, but it's still something worth sort of noting, right? And something that we're going to have to take into account as we're moving forward with things. The low score on this, so I can tell you again, I told you this, so this is data collected in Memphis. Basically, with the film that we were showing them, clip from When Harry Met Sally, the diner scene. You familiar with this? It's fun, right? But it's got Meg Ryan, it's got Billy Crystal sort of in there, right? So we've got two sort of white actors in a music clip in sort of respondents that were sort of have a large proportion of African American folks in there. So think about, okay, sort of people responding to this in the same way. But that scene, if you remember, sort of she fakes an orgasm, and so it's funny, and it consistently elicits sort of amusement from people. But there's a lot of other stuff going on there, right? So we have people kind of feeling maybe uncomfortable or things along these lines, right? So if we think about emotional valence going from 0, not at all pleasant, to 100, so the most happy, sort of pleasant I've ever been in my life, I hope I'm not getting too many of those zeros, right? And it's something that I want to take a look at, but something that we want to start thinking about, right? Does this mean that this sort of didn't work, that this is an invalid response to this, or is this someone who might just be, that might have not been their cup of tea in terms of things that they thought were funny, right? Something along those lines, okay? But in terms of distributions, right? We've got skew, we've got kurtosis. Everything looks to be a pretty reasonable-ish, except for kind of, again, if we're talking about our white non-Hispanic respondents have kind of a high level of kurtosis that's kind of sort of peaked there in the middle. Yeah.
Just a fun fact, it's Rob Reiner's mother that's
that says
director of the
yeah.
and says, I'll have what she said.
Okay, nice, right? If I probably would have told that person, they probably would have scored, they would probably would have given at least a 3.
Yeah.
Right, so they think, that's Rob Reiner's mom. So good. So at least in terms of just preliminary distribution, are we concerned about too much going on right here? No. Probably the biggest thing that we're going to notice here is the unbalanced design. I want to make the note of that. Okay. So doing okay there. What we want to do now is we want to go through and take a look at graphical representation of this. Now what I'm going to do here is I'm just going to go through and I'm going to sort by subject. What does that do if I sort by subject?
Take split files off.
It takes my split file off. If you don't do that, you go through and run it, you get funky things, and sort of like I did, and I'm kind of mad. I'm like, does this new version of SPSS not do things right? I just didn't turn things off. But I'm going to go through, I'm going to go back to analyze, analyze descriptives, and go down to explore. Put valence and arousal as my dependents. Take ethnicity and drop that into my factor list. And then I'm going to take subject number and drop that into my label cases. CJ, why am I dropping subject number into label cases?
It's not coming to me.
Yeah.
To identify the outliers.
Yeah, remember in my box plots. It's good because if we don't do that, it'll just go through and label those circles as your case numbers, and then that kind of gets confusing. So dropping subject numbers down there helps out with this. So I'm going to paste this. Oops. go through the run. Okay. So here is ratings, histograms for emotional valence across my 3 groups. Valence, remember this was the one we had a kurtosis value of about 2. And what I want you to do, I don't want you to spend a whole amount of time, but just give me a general description of what you're seeing in terms of this distribution. Here I would say that this distribution is fairly symmetrical. We've got majority of values falling from 4 to 6, kind of sort of capture that sort of middle piece there. We've got one value falling away from the rest of the lower end of the distribution, right? So just some general things. What I don't want you to do is just identify everything as not unremarkable. Don't do that. If it is, fine, but so this is not an unremarkable distribution. It's got some kurtosis there, sort of kind of a flat thing on the side, so just want to describe that. But any concern about this distribution? No, looks okay. Here, this is our valence ratings for our Black non-Hispanic groups. Again, might describe this as relatively symmetrical, right? Again, with values ranging sort of from mostly from 4 to 6, but not anything too concerned here. This distribution, a little bit harder to describe, right? How might we describe this distribution?
Negative skew.
Some negative skew, yeah. What else?
Multimodal.
Yeah, I might call it kind of bimodal, right? So we've got a major mode at 7 and a minor mode of 4. Generally, if we look overall, it's kind of a square, flatter distribution, even though we've got some stuff there. Right? This one's a little bit more difficult to kind of communicate. And so if you're going through and running through your screening, if you have, feel free to go through and sort of put in sort of actual sort of pictures or graphs so that you can at least communicate this is kind of what I'm seeing, right? Our box plots here, this is looking not too bad, right? I say for white non-Hispanics, that's relatively symmetrical, so not too much going on there. Same thing for our Black non-Hispanic group. Our other group, I'm seeing the median and the 3rd quartile sort of being higher in the distribution, with looks like what might be some level of negative skew going on there. So just trying to talk about some of that. Same thing. This distribution, this is unremarkable distribution, or just unremarkable by the fact that it's a fairly normal distribution, which is nice, right? So this is a kind of a nice normal distribution. Here, I might describe this as another sort of multimodal type of, or sort of relatively normal, but with a mode of 2 or something like that, right? Trying to describe, give that some discussion. Histogram here. Again, we've only got 20 people, so these aren't going to be beautiful and great, right? But so to say maybe a little bit of negative skew onto this. And then with our box plots, our Black non-Hispanic group sort of looking fine in terms of stuff, maybe a little bit of negative skew on our other. Our white non-Hispanic group, there's a little bit of variability, right? The median and our 3rd quartile are the same value in this, right? With what looks to be three values exceeding 1.5 times the inner quartile, and 1 value that's falling below 1.5 times the inner quartile, right? Now the one thing you want to be careful of, how many data points does it look like we're identifying here? In terms of on the upper end, how many sort of values, extreme values are we seeing here? It looks like 3. Be careful because it can start to mask these. If you have too many of these falling on top of one another, it just won't report them. And so if you see that you do have values, and this is pretty clear, right? This is a value of 6. What I can do is I can go through and sort arousal, and I go through and sort this by my ethnicity variable. I can go through and see how many values of 6 that I've got in here, right? So this is my white non-Hispanic group, so my group 0, and I see I've got, okay, actually 3 values here, right? Because sometimes what will happen if I have like say value 1, if I had 5 there, right, eventually it's gonna stop reporting those, it's just gonna mask it over the top. So just go through and double check to make sure that if you say there's only 3 values falling 1.5 times the quartile range, that it actually is. So just double checking that in your data. Okay. Then last, if we go up, we go analyze. We can go through and I'll just take my sort cases, paste this down. So I resplit the file. Z value for valence, Z value for arousal. And then get rid of my skew kurtosis. I don't want that anymore, and I don't want to save Z values on Z values. Resplit my file. Look at Z scores. Anything too concerning in terms of my Z scores, Nick?
Nothing too concerning, but the min is notable for white non-Hispanic, it's beyond 3.
Yeah, so I'd probably here note that my valence, so I have a 4 valence as reported by white non-Hispanics. I've got someone who's scoring 3.25, about 3.25 standard deviations below the mean there, right? Now, if I go back up and I take a look at what that actually looks like, it's this person, okay? Am I concerned about that person in terms of influencing things? Do I need to throw that person out or do anything with it? Probably not, it's gonna be fine, right? But something I would want to probably go through and take a look at. So, based on all of this, on the back of your handout, I have a screening check here, right? So we've gone through, talked about missing data, accuracy, plausibility, distributions, extreme values, and then homogeneity range test. We'll get into that when we actually jump into our analyses. But this would be how I would write up this screening. So again, going through, taking a look, and sort of getting ideas for how these data that we just looked at, how you might go through and describe these within the context of the screening, kind of put it all together. Okay. All right, cool. We made good time today. Get a start on that